This is a straight line. If we consider it to be a set of all real numbers, it will be a vector space over itself with dimension 1. Now if we consider a line segment of that, basically nothing will be changed. But if we bend it just a little, what will its dimension be? In fact, what does dimension actually mean? What is linearity? And how does a straight line help us to determine dimension? We know that on Euclidean geometry, 2 points are enough to draw a straight line. We can consider all these points to be in the space R2 and join some pairs of them by straight lines. So here onwards, without loss of any generality, we will consider all these points as vectors. Now we want to understand this space in a better way, like what are the basic properties all the points have on these lines, and so on. Every single spot represented by a point on this space R2 represents a vector. And by finding the properties obeyed by points on a straight line, basically we can find out the rules and fundamental nature of the space. So let's start with an arbitrary point and consider the coordinate of that point to be xy. That means, on the line, when the point is at a distance x horizontally from the origin, then it will be at a distance y vertically from the origin. As finding the rules followed by points on this straight line gives us the properties and nature of the straight line and the space, we'll try to find out the rules followed by those points. That's why here when x varies, depending on the values of x, let the point is at a height y. That clearly justifies how y is related to x when it is on the specific line. And eventually that determines the relation between x and y. In simple words, we can say, corresponding to every single value of x, the relation determines the value of y, which eventually determines all the points on the straight line. And we can express it as rho of x is y, as y is completely determined by the value of x. Here x becomes the input value and y is its output. And when every single input value has at most one output in a relation, then the relation is called a function. Now on Euclidean geometry, only 2 points are sufficient to construct a straight line, which is a set, collection of all the points satisfying a specific relation between x and y coordinates. If we have the coordinates of these 2 points, then all the points of this line segment satisfy this condition. And you can check it easily, which further gives us y as y1 minus y2 by x1 minus x2 times x minus x1 plus y1. And this arbitrary relation holds for all these line segments here. In particular, we can express this line segment as a subset of the set L, collection of all those x, y in R2, which satisfies y to be equal to y1 minus y2 by x1 minus x2 times x minus x1 plus y1. And without loss of any generality, we will consider the line segment joining x1, y1 and x2, y2 to be represented by the set L itself. Here the set completely depends on the coordinates of these 2 points. And depending on the coordinates in R2 of these 2 points, the whole set varies, and so their representation. In particular, if we consider x1, y1 to be the origin and x2, y2 to be AB, then the equation of the straight line becomes y is equal to b by a times x. That is, Coordinates of each of the points on this line segment is x, b by a times x. For simplicity, we can express this coordinate as x mu x, where mu is b by a. Here all the points on this line segment are of this form, and all the points differ from each other when x varies. So let's consider the coordinate of this point to be x dash mu x dash. Here x dash and x are on the same x-axis, and that's why x dash can be expressed as xi times x, which implies mu x dash is mu xi x, which again can be expressed as xi times mu x. That's why x dash mu x dash can be expressed as xi x xi mu x, that is xi times x mu x. Therefore, we can say every point on this line segment can be expressed as a scalar multiplications of the other one. And extending the line segment to the whole line, we can say in other words that multiplying any point on the line segment by a scalar, we get the point on the same line of which the line segment is a part. Yet the line segment as well as the whole straight line is expressed without loss of any generality by the set L, where y is related to x by mu x. So basically, the straight line L is a graph of the function f maps R to R by f of x is mu x. And correspondingly here, f of x dash is mu x dash, which further implies f of xi x is xi times f of x, which leads us to the definition of a function to be linear. And we will say a function to be linear when it satisfies the condition. And all the points on the straight lines are elements of this graph, which in addition are satisfying the property that each of its points can be expressed as a scalar multiplication of other. Now if we redefine the point on the line segment as v and v dash, then v dash can be expressed as xi times v, which implies v dash minus xi v is 0. And this gives us the condition for two points to be linearly dependent on R2. And obviously, further we can generalize all these things. But for now, we have the basic visualization of how all these things work. Here when two points are on the same line, they're simply dependent on each other linearly. Without loss of any generality, we have considered the points as vectors in R2. That's why the line L represents the set, which is a collection of all such vectors we get multiplying the vector v with the scalars. That is, L is a set collection of lambda v, where lambda is a real scalar. That is, L is a span of v. So lastly, we can conclude here all the vectors on the line are basically dependent on each other linearly, and we can express one vector as a scalar multiplication of the other. But what about the point which is not on the line? Let u be the point not on the line in R2, which simply represents a vector emanating from the origin and terminated at that point. We know R2 is a vector space, and we have only two operations on its elements which are vectors, and those are scalar multiplication and vector addition. And by scalar multiplication of the vectors on the line, we'll never be able to get the vector which is not on the line, and in this case that is vector u. So if we start our journey from the origin along the line and reach at an arbitrary point, say v, then to reach at the point u, we must change our direction towards the point and walk towards that point, which eventually indicates another vector, say w, which also cannot be obtained by scalar multiplication of any vectors on the line. Now, as a vector is not dependent on its position, rather it's completely determined by its magnitude and direction, therefore we can consider the vector W to be emanated from the origin by this one. In similar, without loss of any property, we can shape the vector V also. Then we can see that the resultant vector is a diagonal of the parallelogram made by these two vectors, which are not linearly dependent. And this in fact is the parallelogram property. Here we can have this vector U by adding these two linearly independent vectors, V and W. Now if we consider another arbitrary vector U1 on R2, then we just can scale these two vectors V and W accordingly and add them to have U1. Let us suppose we have V1 and W1 by scaling V and W respectively. Then we get U1 as V1 plus W1, which also can be written as a sum of scalar multiplication of vectors V and W respectively. And let it be some lambda 1V plus lambda 2W. That is, with respect to V and W, we can express the vector U1 as lambda 1 lambda 2, which are the scaling factor of first and second coordinates. Now since U1 is an arbitrary one, therefore all the required vectors of R2 can be expressed as a linear combination of these two linearly independent vectors. And we can express all the vectors as a tuple of scaling factors associated with V and W. Till now we have seen some properties of vectors. So right now, what can we say about linear dependence and independency? We have when two non-zero vectors V and V dash are linearly dependent, then they satisfy the condition V dash minus zeta V is 0 for some non-zero scalar zeta. Generalizing, we get the condition as lambda V dash plus gamma V is 0 when lambda and gamma are scalars which are not zero simultaneously. But when two vectors are not linearly dependent, then we can simply visualize. By scaling both vectors non-zero times, we'll never get 0 as its resultant vector, even if the scaling factor is negative. So this equation determines whether two vectors in R2 are linearly dependent or independent. Here when lambda V dash plus gamma V is 0 for some lambda and gamma which are not 0 simultaneously, then V dash and V are linearly dependent. And when lambda V dash plus gamma V is 0 only for lambda and gamma are 0 simultaneously, then V and V dash are linearly independent. Here you can see all these vectors are same, having little displacements, and all these vectors are parallel to each other. Now if we change the direction of some vector exactly to the opposite and simply consider all these vectors emanating from the origin, we can observe, irrespective of direction, all these vectors lie on the same straight line, even though we change its magnitude. So pair of vectors parallel to each other on the plane are linearly dependent. And simply, we can find out all those non-zero coefficients of vectors which satisfy the equation lambda V dash plus gamma V is 0 to be linearly dependent. That's why to be parallel is sufficient condition for two vectors in R2 to be linearly dependent. So here we can conclude all the pairs of vectors in R2 which are not parallel to each other are linearly independent. Now we have seen we can express any vector on R2 as linear combination of any two linearly independent vectors. So even though three vectors which are not parallel to each other, that is every single vector is linearly independent to each other on R2, we can express one of them as a linear combination of other two linearly independent vectors. From here, we can conclude one interesting fact about vectors on R2, which is any three vectors on R2 are linearly dependent. Thus here on R2, we can have at most two linearly independent vectors. And based on those two linearly independent vectors, we can generate all the vectors on R2. And one such beautiful pair of two linearly independent vectors is the pair of unit vectors along x and y axis. And all these pairs of two linearly independent vectors which generate the whole R2 are called the bases. In particular, the basis having unit vectors along x and y axis is called the standard basis. And with respect to this standard basis, any point or vector AB can be expressed as A times unit vector 1, 0 plus B times the unit vector 0, 1. Since the vector AB is an arbitrary one in R2, therefore R2 can be expressed as a collection of such tuple AB, which is A times unit vector 1, 0 plus B times the unit vector 0, 1, where A and B are real valued scalars. And that is basically the space spanned by the vectors 1, 0 and 0, 1. So simply, a point on R2 which is at a distance A from y-axis along the unit vector on x-axis and at a distance B from the x-axis along the unit vector on the y-axis is represented by the tuple AB. Also, here you can check if a vector space is generated by a basis having finite number of elements, then all the bases of that vector space contains the same number of vectors. And that unique number of vectors of the basis is called the dimension of that vector space. That's why dimension of R2 is 2. Here we have seen different representations of vectors with respect to different bases. But on this lecture series, we will not go deeper than this. Rather, in similar, we can conclude dimension of R3 is 3 and dimension of Rn is n for all n in the set of all natural numbers. And now, we'll try to have a deeper look at the distance in R2 and so on in the very next lecture.